thank the organizers for inviting me and for putting this very nice workshop on hydrodynamics in those challenging times. Today I want to tell you about some recent but not so recent work on superdiffusive hydrodynamics in quantum spin chains. So it's a topic I've been working on for like a few years now. It's also a recurring topic in this workshop. You heard about this already from Joel Moore yesterday. I think you'll hear even more about this from NA later this week. My goal here in this talk will be to try to give you some kind of overview of what this is about. And I'll try to summarize our understanding, or at least my understanding of this phenomenon using a simple quasi-particle picture. Okay, so apologize to the experts. I will mostly try to give a broad overview if you don't know this topic. But I hope to spend some time on the last paper I'm quoting here, which is very recent and has to do with integrability breaking and the stability of this phenomenon. Okay, so we have lots of time, so please interrupt me if anything is unclear. Okay. All right, very good. So let me start by thanking my collaborators, my postdoc, Braden Ware, who has now moved to University of Maryland. My main collaborator on those topics is Sarang Gopalakrishnan, now at Penn State, and more recently, the works I'm going to tell you about also involve Jacopo Denardis and Eneli Ilievski, both of whom are in the audience and also speaking on different or related topics. Okay, so you can ask them questions if I say some nonsense because it's too early for me. Okay, so let me start with a just very brief introductory slide, which is probably not necessary given the audience. So I'm going to be talking about spin transport. And so I'm not going to talk about anything far from equilibrium. I'm just going to talk about linear response, right? So the typical setup I'll have in mind is just a spin chain. I'll be working in 1D. I'll be talking, what I'm going to tell you about applies to both quantum spin chains or classical spin chains. Spin, I'm going to work in systems in which spin is a constant quantity, and imagine, you have a setup where you have different reservoirs, maybe on the left and on the right, with maybe different magnetization or magnetic field if you want, and you just wait long enough in your system, and you just wait for some current flowing in your system. Okay, and I'm going to think of a setup in which the imbalance in magnetization is relatively small. Okay. Equivalently, I'm really going to think of just, again, linear response to a local perturbation. So I'm just going to imagine taking my spin chain or my 1D system and having a slight magnetization excess somewhere. And just, the main question I'll try to address in this talk is how that perturbation is spreading with time. Okay. And just to remind you, the expected behavior that, expected from hydrodynamics that just follows from power counting are diffusive. So that's, of course, the case we all learn about first, right? Just fake Fourier's law, finite conductivity, dynamical exponent 2 in the equation I have here. Another kind of generic answer that's at least particularly relevant for integrable system is that of ballistic transport. So dynamical exponent 1, it basically corresponds to having a velocity. Yeah. And so anything that doesn't fall in those categories, we usually call anomalous diffusion, or at least I do. In particular, anything between diffusive and ballistic will be superdiffusion, and anything slower than diffusion would be subdiffusion. Okay. All right, so that's it for just basic terminology. The other thing that we can probably all agree on, because I think there's mostly low-dimensional people in the audience, is that 1D is special. So we all know Luttinger liquids. We don't have Fermi liquids in 1D. There's many body localization, for example, which I'm not going to talk about at all, which is also kind of something we believe is specific to 1D. And for this crowd, we all know that, say, just even conventional hydrodynamics of gases and fluids is also special in 1D, right? And that it breaks down, or fluctuations are relevant if you want. And I think we'll hear even more about the breakdown of hydrodynamics in the next talk, okay? So we all know that, special things can happen in low dimensions, in particular in 1D. And so in some, well, in a clear way, I think like the story I'm going to tell you about is also relying on this fact that 1D is very special. Okay. So anyway, this talk is going to be about superdiffusion in a broad class of spin chains. Actually, really most of this talk is going to be about just the one spin chain, just this Heisenberg spin 1/2 antiferromagnet quantum spin chain. So again, if you attended Joel's talk yesterday, this slide is going to be an entire repeat of what he already said. But let me go through this for completeness. So what's the claim? So the claim is as follows. So you take this very simple antiferromagnetic spin chain. I should really emphasize this is a very well-known model, right? It's not like we discovered it yesterday. There are many books, entire books and chapters on this model. We know a lot about it. It's been studied by many people. And spin transport is not really an exotic question. So you could have thought we would know everything about this, right? But the claim is that there was a surprise, at least a few years ago. So I'm quoting this paper from the Ljubljana group and Tomasz Prozen's group. I should say there were earlier paper by Marcos Niederich in particular, but really I think this paper is the one that kickstarted this whole field. And so the claim, which is numerical, is as follows, is that if you study spin transport in that system, numerically it looks like it has superdiffusion with an exponent 3/2. Okay, so the way I'm showing data here, that's borrowed from that paper. This is DMRG. And so the initial setup is, this is time, this is space. You have actually a kind of domain wall initial state where you have a higher magnetization on the left than on the right. The initial state is actually a mixed state. It's actually at infinite temperature. So don't think this is just a domain wall of spin up, spin down. This is really mixed, and this is a high temperature state. And you let that domain wall melt under time evolution. Okay, so this is time. And what they observe numerically is, again, the way it spreads with time is faster than diffusive, but also very clearly not ballistic. You don't see a straight line or velocity here. Okay. And so when that paper came out, and I should say again, there were already signs of this in the early literature, but I think really many people, including myself, really realized this fact after reading this paper. I think many of us were really shocked or like intrigued about why this was true. Again, just to emphasize, this is a very well-known model. It's the Heisenberg magnets. Like, what else, can we learn about this? At low energy is described by a Ledinger liquid. And so you would think Ledinger liquid would tell you what's going on. So I should say this is at high temperature, but it really works at any temperature. And it really came as a surprise. And so by now it's been reproduced by many groups, right? So this is not a numerical issue or anything like this. There's been numerous papers. I'm just quoting data from this paper here. This is just another way to plot the same thing. This is kind of a conductivity as a function of time. So think of it as a time-dependent diffusion constant, if you want. And what they observe numerically is, so actually you should focus on the left here first. It grows as t to the 1/3, which is the same exponent as here. And you see it's true for any temperature, right? So it's true at high temperature, and it's also true at very low, relatively low temperature. Okay, so for all time scales you can access, it looks like this t to the 1/3. So one thing I should say right away is like, okay, the spin 1/2 antiferromagnet is integrable, and this will play a key role in the story. However, if you do the exact same numerical experiments for the spin 1 Heisenberg chain, which is now gapped and is not integrable, you can look at the curves yourself. It looks fairly convincingly proportional to t to the 1/3 again, right? And it looks that you see the same exponents, again, in a broad range of temperatures. So I'll come back to this. I'll try to explain this. Okay. All right, so that's the claim. I'm going to go back. I'm just going to go back to the spin 1/2 Heisenberg version. So this point, this Heisenberg point, where you have this SU2 symmetry, there's also a sense in which you should think of it as a dynamical phase transition. Okay, and so by now we kind of understand the different phases, quote unquote, quite a bit in terms of spin dynamics. But just a few years ago, this was mostly numerical. And so if you put some anisotropy here in your spin chain, it becomes the x-axis spin chain. If delta is less than 1, it turns out that spin transport ends up being ballistic. So this is kind of what you would expect from, again, Luttinger liquid theory, and from the fact that, again, this is an integrable model and you have many conserved quantities. So ballistic sounds like kind of the expected answer here, but I should say this phase is actually very rich, and spin transport has a long history here I'm not going to talk about today. But there's a fractal judo weight, and there's also anomalous diffusion and corrections in that phase. If delta is larger than 1, well, spin transport happens to be diffusive, okay? And so we've had evidence, numerical evidence for this for quite a while now. So this is numerics from a paper from 2014. This is DMRG data. Again, this is space, this is time. And this is, for some value, delta equals 1.5. And what you're supposed to see here is like, if you prepare some kind of energy excess somewhere and you look at the way it spreads with time, it looks ballistic, right? There's kind of a straight line here. But if you do exactly the same for the same parameter for spin, okay, well, it's maybe hard to fit this in your head, but it looks diffusive. Okay, so you can rescale this. It looks like a perfect solution of a diffusion equation. Okay. So this has been a mystery for some time. I think now we understand it pretty well, and I'll tell you some things about this. So, it looks like you have spin diffusion that coexists with the fact that energy transport is ballistic. Okay, and again, this is, I'll talk about why this is true. It's fairly well understood by now. And so, what's interesting here is you should think that that point like this, where you have superdiffusion, is really a phase transition between the two, right? So, you may think it's not so interesting because we also have a phase transition in the ground state of this model, right? So we have a Luttinger liquid to a gapped phase at delta equals 1. You go to a Néel state for delta larger than 1. But here, like, this is a phase transition in 1D that occurs at finite temperature. So the type of transition that you read in textbook should not happen. And it happens even at very, very high temperature, including infinite temperature. Okay, so if you look at spin transport, there's really something dramatic that occurs as a function of that parameter delta here. Okay, so again, you heard a bit about this from Joel yesterday already. So it's not only that you have an exponent we have, there's also good numerical evidence by now that this falls in the celebrated Cardar-Parisi-Zhang universality class of KPZ. Those are collapses you saw yesterday. And so more precisely, the claim is that if you look at a spin-spin dynamical correlation function or structure factor, right? So correlation of spin at position 0 in time 0 and spin at time t in position n here, this obeys a scaling form at long distances and long time that falls in that KPZ universality class. So you not only have that exponent 3/2, you also have a whole scaling function which is not Gaussian, and which, and again, is compatible with KPZ. Okay, and so this suggests some kind of emergent hydrodynamics for the magnetization or spin in this model, which I'll talk about later. Okay. All right, so there's a claim. Let me mention experiments, of course. Again, the first one I'm not going to talk about at all because you heard extensively about this from Joel. So by now, there are like 2 experimental setups that observe this. One from neutron scattering in real solids, again, even almost at room temperature. And again, I refer you to Joel's talk on this yesterday. And even more recently, just a couple of months ago, there was also a paper from Cold Atoms from Emmanuel Bloch's group, where they basically did that setup, the same setup you had in the Ljubljana group numerically. Essentially, they have like a domain wall initial state and they look at it melting And they observe again that exponent 3/2, but they can also observe really the fact that the distribution is non-Gaussian. So they really probe more the KPZ scaling function because they have the full, they have the full profiles. So they could go beyond this. Okay. All right, so by now this is well established both numerically and also experimentally, and it's something you can observe, even in real solids at room temperature. And so the last piece of information, so for now I'm not explaining this phenomenon at all, I'm just giving you the phenomenology that we have numerically, is that this is not limited to the Heisenberg chain. So this is mostly just to advertise NS talk later this week. And so, there's some early observation from the paper by Maxime Dupont and Joel Moore and several other papers. We have lots of evidence by now and also some good theory arguments that you'll hear from Ene that this superdiffusion is super universal in some way. It shows up in many models, just the Fermi-Hubbard model, if you don't like Heisenberg for some reason. It shows up in Fermi-Hubbard. It shows up in many spin chains with different non-abelian symmetries. So it's really a robust phenomenon. Okay, and there's also a sense in which it survives integrability breaking, and I'll talk about integrability in a minute, up to long times. And hopefully I'll have enough. I'll spend some time discussing this later. All right, so that's pretty much the summary of like where the what the state of the numerics and the experiments is. So the claim is that we have a superdiffusive transport that's observed in a very large class of quantum chains. I wrote here quantum, it's actually not necessary. Again, we also have numerics in classical spin chains where you observe the same thing. But I'm going to be talking about quantum systems exclusively here. What are the key ingredients? So what we know is that we need some kind of isotropy in a spin chain. So meaning you need a non-abelian symmetry. So in the case of Heisenberg chain, you need this SU2 symmetry. So how do we know this? Well, if you break that symmetry, you see the superdiffusion go away, right? So we see this pretty easily in numerics. I already mentioned in the phase diagram here, if you put this anisotropy, you break the symmetry and you see you get either ballistic or diffusive. So really you need that non-abelian symmetry. So if you put a tiny magnetic field, for example, this whole superdiffusion goes away entirely. So that's one key ingredient for sure. And another ingredient is integrability. Okay, so how do we know this? This is a bit more subtle. So, like the spin 1/2 Heisenberg chain is integrable. The models I was showing here, like the Fermi-Hubbard model, is also integrable. But I also showed you numerical data of the spin 1 Heisenberg chain where we also see the same type of scaling, even though it's non-integrable. Okay, and as you heard from Joel, we also see this in real, solid state systems close to room temperature, and there are certainly a lot of non-integrable things going on over there. Okay, so again, the story here is a bit more complicated. Integrability is crucial, but it's also very stable against integrability breaking will be the main story. Okay, so how do we know that integrability is crucial? I'll comment more on this later. We have examples of systems that have SU2 symmetry. A typical example would be a random quantum circuit, for those of you who like quantum circuits, with SU2 symmetry, and you can show spin transport is diffusive there. So we definitely have counterexamples. You don't need only non-abelian symmetry to get superdiffusion. All right, and so the question I want to address in the rest of this talk is, how do we understand this? Okay, so given all this information, like how do we come up with a theory of this? And the thing I'm going to try to do is start from this integrable case, this Heisenberg spin chain, give you some sketch of the argument of what we think is the physical mechanism for this z equals 3/2, and to some extent this KBZ scaling. And then I'll spend some time adding perturbations and explaining how that survives. Okay. But maybe it's a good time for me to just take a quick break and ask if the setup, or just at least there's any question about the numerical data or anything I just said.
So, Roman, one question was, so I thought you said that spin one still shows super diffusion, right?
Right, yeah.
But that's not integrable, right?
Correct. Yeah, so numerically, it looks like it shows super diffusion. What I will argue later is that, at least I believe that eventually it will cross over to diffusion, but that you'll see the super diffusion for a long time. Okay. And how long is actually an open question. So I'll get to this, but yeah, the general belief, what I believe is that you need integrability for this to go on forever. However, you see this 3 halves in many systems, including pretty non-integrable ones, which I think is interesting, right? Because it's very robust, and like you don't need to be very fine-tuned to integrability to see it.
And Homa, when you say the integrable, you mean through the Bethe sense or through the locally conserved quantity sense? So I know that spin half is the Bethe integrable, but spin one, you don't probably have the Bethe on that.
So when I say integrable, I mean in the, okay, I don't want to talk about various definitions of integrability, but I'll mean like really young Baxter Bethe ansatz, like actual.
Okay. Not the local conserved one. Okay.
No, yeah, not like a local, not like localized or anything like this. Yeah. I want like Bethe ansatz integrability, correct?
Okay. Thanks.
Yeah.
And if, for instance, you have really extreme domain wall, plus magnetization plus 1 on one side, minus 1 on one side, on the other. So do you now perfectly understand what's wrong with that setup?
Very good. Yeah.
It's not T to the 2/3.
Correct. So indeed, if you do this, it's a different type of setup. You don't get 2/3, you get diffusion with log corrections, and some people in the audience have worked on this more. So you need an initial state that's at finite entropy density. So you want like a finite entropy initial state. You want something that's not like that, in the story, you'll see you need really hydrodynamics. I want to be at finite temperature if you want. And so that domain wall initial state, you're locally in the vacuum, right? So it's really more like you're locally in the ground state with all states are up, locally in the eigenstate with all states are down. And so it ends up being special. So yeah, the argument I'm going to tell you is not going to work for that domain wall initial state. What the full theory of that domain wall initial state, I'm not going to talk about. And like I said, there are people in the audience that would be more qualified to talk about this. But yes, correct. I want a mixed initial state. I want something at finite temperature. Thank you.
Romain, sorry, maybe this question was already asked, but so suppose you break integrability by adding perturbations, but still adding only terms which still maintain SU2 symmetry. Do you lose the anomalous behavior?
Very good. So, well, like, okay, you're like way ahead of me. So this is like the end of my talk. I'll have slides on this, but yes, like it turns out to be very robust if you preserve the symmetry. So I'll talk about this. You're just you're just ahead of me. But yeah, that's a very good question, and the answer is yes, the symmetry will matter, and I'll talk about that.
I see. So it's more of symmetry than integrability, right? It's symmetry.
It's both really, but there are different ways of breaking integrability, and preserving the symmetry will make this very robust.
Okay. Thanks.
So that will be one of the main points I hopefully make in this talk. Yeah.
Okay. Thanks.
Yeah. All right. So how do we understand this in terms of theory? So let me just mention generalized hydrodynamics, really to give credit to those 2 papers that really changed the way we think about integrable systems. So the argument I'm going to tell you in some way goes beyond this theory of generalized hydrodynamics. And again, you heard about this yesterday already from Jacopo and Joel in particular. So in some way it's going to go beyond, but it's really like based on the basic ideas of generalized hydrodynamics in the sense that, I'm going to rely a lot on the intuition that those 2 papers gave us. And in particular, like, you can think of this generalized hydrodynamics as quote unquote just hydrodynamics, but applied to integrable systems where you have all those conserved quantities. But what you heard already a bit yesterday is there's a sense in which you can think a bit more like intuitively, let's say, of this generalized hydrodynamic framework as some kind of kinetic theory for the quasi-particles of integrable systems. So at least that's the way I like to think about it. Integrable systems have quasi-particles, like solitons if you want, but like a quantum version of them. And you can think that this theory of GHD is essentially like tracking down or taking those solitons or quasi-particles very seriously. Okay. So again, you don't need to know any generalized hydrodynamics to follow the argument I'm going to give you. And so again, for now, I'm just going to focus on the Heisenberg chain. And we're basically going to follow a route which is also kind of based on what you would do as a just condensed matter theorist, that is to think of just quasi-particles and try to think of transport in a quasi-particle way. Okay. The only thing special here is because the model is integrable, those quasi-particles are stable and they exist at any temperature. Okay, so not only at low energy. Okay, so what are the quasi-particles of this Heisenberg chain? Well, they're called magnons and strings. Okay, so if you're Bethe-Ansatz experts, you can ignore the like very cartoonish pictures I'm going to show. If you're not a Bethe-Ansatz person, like intuitively what you can think, and I'm going to, I actually want to think of quasi-particles above like a finite temperature state. But I'm going to simplify the discussion just to, at least for the intuition, and just think that, okay, we're just going to think of a reference state, which is, say, a vacuum where all spins are aligned. There's some gauge choice here, which will actually matter. I'll come back to this. And what are the excitations above this? Well, they're magnons, okay, that we're all familiar with, that carry spin 1. I'm going to label them S equals 1. And they're also bound state of magnons, which here I'm drawing in this kind of cartoon way. S equals 2, a bound state of 2 magnons, and S equals 3, a bound state of 3 magnons, and so on. And all those magnons, which also called strings, they're stable quasi-particles at also finite temperature. Okay, so of course the cartoon picture that I'm drawing here is not really correct once you think of finite temperature, but it will just be useful nevertheless just for the intuition. Okay, so you have those magnons and bound states of magnons or strings that are really quasi-particles. And so, the only thing that you'll really need here for the argument is like, in some way, like the nice thing about generalized hydrodynamics is I think it taught us to think about those quasi-particles very physically, in that basically you should think you just have a gas of those semi-classical particles, and they have some density, which we know from thermodynamic Bethe-Ansatz. They have some group velocity and they carry some charge. Okay, so the density happens to scale as 1 of S cubed, for example. The velocity goes as 1 of S. All those things are fairly well-known results that you can derive from just from Bethe-Ansatz. And those magnons, you will not be surprised, they carry some spin, right? So a magnon is a spin 1 object. And S here is really the charge or the spin of those quasi-particles. Okay, and so the claim is you have those objects that move and they never like backscatter or anything like this. They kind of like dress each other, if you want, through interactions, but otherwise they keep moving, basically ballistically. So, okay, so now like we have quasi-particles, they move ballistically, we have nice semi-classical objects. So if you don't like quantum mechanics, you already mapped things to essentially a classical problem here. But we have like ballistically moving quasi-particles, okay, and they are charged. So if you think a bit about it, it sounds like spin transport should be also ballistic, right? So you have something moving, it carries some spin and carries some energy too. So naturally, you would expect that any transport would be ballistic. And that's in fact what you expect for most conserved quantities or in integrable systems. But there's another ingredient, which I think the key ingredients, at least in the way we understand it, which is screening. So Basically, the idea is that those magnons or like bound states, as they move, they become screened by the environment, at least if you're exactly at the SU2 points, that, let's say you're half filling in terms of fermions, so you don't have a field. Okay. So how can we see this? And again, I'm going to show a cartoon, and you'll have to trust me that, you know, this is true in more generality. So let's think of a magnon moving through a sea of, say, spin up. So let's say you have a spin down. So it's a magnon excitation. And let's say it moves through a sea of spins up. And I'm drawing things, again, semi-classically, so you can think of it as some kind of cellular automaton if you want, where just classically you flip-flop that spin and you kind of move it, you know, by one step every time, right? So here it moves left, for example. Right? And you ask, okay, what happens when it collides with a domain of spin down, which in my language would be a bound state of magnons, which here I'm assuming are immobile in that picture. Okay, so you think about what happens. And again, there's no backscattering or anything like this. What actually happens in terms of solitons is you're actually going to flip those two spins in the middle here. And now there's actually a spin up that propagates through a sea of spin down. Okay, so I'm just going to show the picture again. So you had that magnon that was a spin down moving in the sea of spin up. And now it collides, if you want, with that sea of spin up. And so what happened in the process is that magnon converted in now a spin up moving in the sea of spin down. And there was also a phase shift, if you want, like the big domain also shifted by two sides. Okay, so this is semi-classics. It was pointed out in earlier papers. This is not new. There's this there's this paper called quantum bowling, if you want to see it. So they had more numerics on this. This is a fairly well-established semi-classical phenomenon. But what it tells you here is, like, if you think of the magnon, right, it started as a spin down, but now it's a spin up, right? So meaning really it spans, like, if you think you're in a system where it's like you have those domains and you're at half filling, so meaning you have SZ equals 0 on average. If you think of the magnon moving as it propagates, it will spend half of its time being up or half of its time being down. So if you want, its charge is kind of oscillating as a function of time. So importantly, yeah, so this turns out to be really one of the crucial ingredients of this dressing. So this is also an ingredient of generalized hydrodynamics. Generalized hydrodynamics predicts this dressing and tells you that indeed, like, the actual, even though you had that charge for the magnons and the quasipart and the bound state of magnons, it's actually, the dressed charge is actually 0. So it's there's some dressing by the environment where you actually lose your magnetization. But here, like I said, like the way I'd like to think about it here is kind of like as a dynamical process. And again, if you're not convinced by the cartoon, okay, like you have to trust me that the cartoon tells you also what happens in a more complicated state where, you're at finite energy density and so on. But basically what it tells you is that those quasi-particles and those bound states, which I'm labeling by S, right? So they move ballistically, but eventually they lose their charge. So as they move through the system, their charge will kind of oscillate. So if you want, they will become depolarized or they will become screened. And eventually they will not contribute to spin transport. Okay. And so how do you get screened? Well, you get screened by when you collide by a quasi-particle bigger than yourself. So you can kind of see it here. You had one magnon moving through a big domain. And in general, what happens is you start colliding with something bigger than yourself. So how long does it take? Well, you can do a back of the envelope type of calculation. We have the density of all those quasi-particles. We have their velocity. And so it takes some time, if you want, for a quasi-particle to actually get screened. Okay, and this time scales as S cubed. So let me unpack. So this is fairly large for S is large. And the reason it's large is because those quasi-particles are slow and because those big quasi-particles are also not exactly dense, right? And they are pretty rare. So it takes time before this screening occurs. And so this time scale actually ends up being really, so the cube here ends up being key. So it's actually the same cube in this dynamical exponent, as you'll see in the next slide. So this is really the main mechanism that's going on here. You have quasi-particles, And initially they carry some charge, and as they move, they again lose their charge and become depolarized, okay? So as a function of time, you'll have bigger and bigger quasiparticles that will contribute to transport, as the smaller ones will be completely screened. And the bigger ones are actually very slow or very rare, okay? All right, so this argument that I just gave you, which admittedly is a bit hand-wavy, and we have several versions of it, some of them more or less precise or rigorous. So I'm giving you a fairly hand-wavy version for this presentation, but which I hope is intuitive. So at time t, only Magnon bound states with S equals t to the 1/3 contribute to transport. So that's the claim. So that was the one technical argument of this talk. So Magnon, strings or bound states that are smaller than this are completely screened. Okay, so they don't have a charge. So say if you think of a single Magnon, for example, very quickly it will become screened and it will lose its charge. Okay, so it's moving ballistically, but effectively it has become neutral and you can drop it. Okay. And quasiparticles are a lot bigger than this. They are not screened, but they're also very, very slow. Okay. And so effectively this scaling is really key to this anomalous transport. So you end up having those bigger and bigger quasiparticles as time grows that contribute to transport. And so this is an argument we had with Sarang, I should say, like the scaling of the time scale. And here I'm presenting you a more like recent version we had in that latest paper. Okay. So that's it in terms of physics. So now you can actually kind of put this, if you want, in a kinetic theory. And so this is just the one equation of this talk. I'll go quickly on this. You can put this in a Kubo formula. Think of it as a normal Boltzmann equation. That is enough to derive this Z equals 3/2. Okay, so you say your transport or your current is just given by quasiparticles. Here, treating them as classical, it doesn't really matter. You have density, you have matrix element of the current. And crucially, you have a screening aspect here, just telling you that, again, the contributions are kind of, if you want this, there's some kind of effective lifetime of those quasiparticles in the way they contribute to spin transport. So even though the quasiparticles are infinitely long-lived, they only contribute to transport up to some time scale, which is the screening time scale. And if you compute that integral, put everything in there, you see that the conductivity is diverging as omega to the -1/3. And this omega to the -1/3 is precisely the Z equals 3/2 that was seen in numerics and in experiments. So that tells you Z equals 3/2. Okay. So that's the main argument. And again, we have several versions of it, but really one of the key ingredients is this screening. Okay. So that's one way we understand it, and it's purely in terms of quasiparticles. You'll notice like integrability really plays little role in the argument I gave you. It really plays the role that those quasiparticles are actually stable at any temperature. So they don't have a lifetime on their own. Otherwise, I would say it's a fairly standard, kind of condensed matter Boltzmann type argument in that it's just following quasiparticles and seeing what they do. All right, so perhaps a natural question here is like, okay, but where does KPZ come from, right? So we talked about KPZ, you heard about KPZ yesterday. Why do we have KPZ universality class? What I told you about doesn't tell you anything about this. So briefly, let me mention, there's a nice argument from Dhar, who's also a speaker at this conference. So you can see people working on this are pretty well represented among the speakers, I guess. And his argument is roughly that in the way I constructed the quasiparticles, or the way you construct them in Bethe ansatz, you have a reference state where all spins will align in the same direction. And so Dhar argued that this reference state gives you some kind of gauge degree of freedom that has its own hydrodynamics. And through some, so there are some steps, some of them we're hoping will eventually be made more rigorous in the future. You can actually derive a Noisy-Burgers equation for the motion of this gauge degree of freedom. And that would explain this KPZ universality class. I should say that like here I talked about those, in the version I gave you, we have like those giant quasiparticles. So I say giant because you see S grows with time. So you have really big bound states of magnons that end up contributing to transport. And so there's a nice mapping actually between those giant quasi-particles and those kind of goldstone soft modes like slow vacuum rotation that we argued is responsible for KPZ. So there's kind of a nice connection between the two. And maybe NA will tell you more about this in a couple of days. So let me mention that even though the argument I gave you is pretty hand-wavy, we can turn it into more quantitative predictions. So for example, we can even compute the KPZ coupling or the superdiffusion constant if you want. So we have even order 1 prefactors. So here is some numerics. You can focus on the figure on the right. This is some quantity which is normalized so that at long times it gives you an order 1 number, which is the KPZ coupling. And the dashed line are the theory predictions at different temperatures, and that matches pretty well the MRG data. This is yet another plot of this in a more recent paper. So this is a diffusion constant as a function of time, plotted this to t to the 1/3. You see it's a pretty good straight line in numerics. But we also have like really putting, working a bit harder than what I just told you. You can even get, again, prefactor here. So this is at infinite temperature. You see, you just have like a number. And, if you compare to numerics, you see the fitted slope and the theory slopes are less than 1% from each other. Okay, so this is just at least to convince you that we understand this, well enough at least to make quantitative predictions. None of what I told you is rigorous. There's definitely really building on things we don't have yet in generalized hydrodynamics. So maybe down the line, we'll have a more precise and more rigorous understanding of this. But we certainly understand this enough to make quantitative predictions. Okay. Maybe I actually want to talk about integrability breaking, so I'm going to skip this real quick. So this is just to mention that if you break the SU2 symmetry, you get regular diffusion, and we understand this pretty well by now as well. So if you break the SU2 symmetry, if you make delta larger than 1, now the quasi-particles end up having a velocity that decays exponentially. So this is kind of clear in perturbation theory. If you have like big bound states of magnons, you need to go to high order in perturbation theory in one of the delta to move them. And so as a result, this kills everything I just told you, and you get a nice diffusion constant that you can compute analytically and was computed in those papers. This is a plot of what the diffusion constant looks like. It blows up at delta equals 1. But if delta is larger than 1, we just have regular diffusion. Okay. Maybe I should point out that it's nice there are not so many quantum, interacting quantum systems in which you can compute the diffusion constant exactly. And so this is one example where we think, like the formula I wrote here, we think is the exact answer at high temperature for the diffusion constant. Okay, so in the last like 10 minutes or so, I think, if I'm counting right, of this talk, let me just talk a bit about integrability breaking, which I think is the more recent topic. So it's something we published just a few months ago, and which I think is more interesting and is even harder to tackle. And it has to do with the stability of what I just told you, right? So integrability is needed to have those very big bound states of magnons contributing to transport, right? So if you don't have integrability, you don't expect bound states of 1,000 magnons to dominate transport, right? You would expect those bound states to die very quickly. But one mystery that I already discussed a little bit, right, is that this superdiffusion appears to be very robust. Again, we see it in experiments. We see it in actual solid state systems, which are very much not integrable at 300 Kelvin. And we see it also in the spin 1 Heisenberg chain, which is very much not integrable either. Okay. And so this is a bit of a mystery. So you could think maybe the story I just told you is irrelevant. Maybe you just like need SU2 symmetry and no integrability. So that is not the case. There's this nice paper by Andy Lucas, the next speaker, on just developing, just SU2 hydrodynamics. And they confirm that if you do just SU2 hydrodynamics, no integrability, you just get diffusion, nothing else. Okay. So maybe it's obvious to you, maybe not, but just having non-abelian symmetry is not enough to get something super exotic like this KPZ. So you need something being close to integrability. So what happens when you break integrability? Okay, so qualitatively, the main difference in what the main thing that will be affected in what I just told you is that the quasi-particles will be able to decay. Okay, they can have a finite lifetime. Okay, so all right, and how they decay? Well, at least you can estimate in a Fermi-Golden rule way. So if you want, you can really write a Boltzmann type equation. Okay, except you don't start from non-interacting particles. Similar if you want to the Boltzmann equation, you would write for Fermi liquids. Here you write a Boltzmann equation for those integrable systems where you have a collision integral, if you want, that will make your quasi-particles decay, okay, or that will break integrability. And that, we don't need the precise collision integral here. Like roughly, like the only thing I will need is that, the rate at which those quasi-particles will decay is given by Fermi-Golden rule, that is to say it will have a matrix element squared and some density of state factors. So now if you break integrability in a brutal way, that is to say, let's say you have, what we did in numerics is we put actually classical noise coupled to SZ. Okay, so it breaks the SU2 symmetry, breaks everything. You can convince yourself that the quasi-particles will decay very quickly. And in particular, those giant quasi-particles will just decay. And what it means is that now you should expect diffusion. And that's what we find numerically. So this is a plot of a diffusion constant as a function of time. Okay, so I'm kind of skipping how we actually extract this. This is an effective time-dependent diffusion constant, and you see it just saturates. Okay, and gamma here is the strength of the noise. So even for tiny noise, on a time scale of 1/gamma here, you just saturate to a constant and you just get vanilla diffusion. Okay. So everything I just told you about goes out the window. It's not stable. It goes away, and you don't see KPZ. You just see diffusion. Just very briefly, let me mention that, okay, even if you see diffusion, the diffusion constant, at least the way it depends with the integrability parameter, is non-analytic, and it still has that exponent 1/3. So if it's any consolation, you get diffusion, but at least the way diffusion scales has signatures of SZ equals 3/2 again. Okay. But okay, let me come to the more interesting point. So now let's do something a bit less brutal. Let's think of perturbations that preserve the SU2 symmetry. Okay. So like here, the key point is like those giant quasi-particles I told you about. Again, when they become very big, they map onto essentially slow vacuum rotations. Okay, so they look like, if you want, almost Goldstone modes. They kind of, we like to call them Goldstone solitons. So they're basically solitons, like quasi-particles. They move ballistically, but they have the kind of slow, soft vacuum rotation, meaning they have low energy. And so not only do they have low energy, you can convince yourself that if you act on such a slow vacuum rotation with something that preserves SU2, the matrix element is going to be very small. Okay, so I don't know if this is intuitive to you, but like Goldstone modes are low energy excitations, right? By definition, they have very low energy, but they have very low anything that's SU2 invariant, right? Because locally you're very close to the vacuum, so anything that's SU2 invariant is going to have a very tiny matrix element. And so more precisely, if you have like one of those Goldstone type quasi-particles of size S, the matrix element you can show is suppressed as 1/S. What it means is that when S is very large, that matrix element of the perturbation that enters Fermi-Golden rule is very small. And so that can suppress the rates at which the quasi-particles decays. And that can make those quasi-particles very stable. Okay. And so this gives you a bound on the rate, and like there are density of state factors, and this is the part that's a bit harder to deal with. You can convince yourself can only suppress this further, okay? And so in particular, if you just break integrability in this Heisenberg chain, and so here we added, for example, next nearest neighbor interaction, we also tried staggered couplings. You still preserve the SU2 symmetry, but you can break integrability in a pretty brutal way, right? You can go far away from that special point. Well, okay, granted, those are relatively short times. Those are times you can access with DMRG. You see a diffusion constant that grows with t to the 1/3. Okay, even if you're pretty far from integrability. So this is very different from that picture I showed here, where you see the diffusion constant was just saturating fairly quickly. Here, we really don't see it. Even if we crank up integrability breaking, you just see t to the 1/3 again. Okay, the plot on the right is an effective dynamical exponent as a function of time. And you can see it seems to approach 3/2 pretty well, even though you're not integrable anymore. Okay, and so ultimately the reason is that those quasi-particles are very stable, at least perturbatively. So I should say what I'm doing here is a Boltzmann approach. So I have a Fermi golden rule and so on. Eventually, I believe you should reach diffusion. What I'm claiming is that at least the timescales that are involved go beyond Fermi golden rule. So if you want, you need to go to higher order in perturbation theory, or you need even non-perturbative processes maybe to destroy those giant quasi-particles. So this is my last slide. Let me just mention that, okay, you can make this a bit more brutal. You break the SU2 symmetry, but you add noise. This is to say, like, no, energy is not conserved. So you still have this physics that the matrix element is suppressed, but now the phase space is a bit bigger because you have many processes that don't conserve energy that are allowed. But nevertheless, the giant quasi-particles are still long-lived. So the rate at which they decay is still suppressed. Okay, so this is simple Goldstone physics if you want. So there's still a bound. Like if you take S very large, that rate is very small. Okay, so those giant quasi-particles that are responsible for superdiffusion are very long-lived and stable. And they give you divergent contribution to the low energy conductivity. And so in this case, you can do that calculation. I refer you to that paper if you're interested in the details. And you find that if you have noise, you get log superdiffusion. That is to say, you get a divergence of the conductivity, but now it's only logarithmic. So this is almost diffusion, right? But up to a log. So, and it seems to work pretty well against numerics. So this is, again, a time-dependent diffusion constant versus log of time. When here, so we're doing noise coupled to energy density, and the inset is noise coupled to energy current, both of which are SU2 invariant. And we see when the noise is small, the diffusion constant is, reasonably proportional to log t, I would say, for several decades. Okay. However, you see that when we crank up noise, we see pretty clear signs, I would say, of saturation. Okay, so this is just to emphasize the story I'm telling you here, this actual divergence, it's only what we get doing perturbation theory, right? So I'm not claiming, I actually believe that you get diffusion whenever you break integrability. But probably to see diffusion, you need to go to higher order. You need to do something more involved than what we did, which was just this Fermi golden rule approach. All right, so let me wrap up so we have time for questions. So hopefully I've convinced you that we have some interesting anomalous superdiffusive transport in integrable isotropic spin chains. Again, you need integrability and you need isotropy or non-abelian symmetry. Those are two key ingredients, at least in the way we understand it. Okay. There's a relatively simple mechanism that I tried to sketch. Integrability is only needed to stabilize the quasi-particle. So I should say, you probably noticed that in my argument, I didn't need a lot of beta ansatz or anything like this. I only needed a couple of inputs from integrability. Really, integrability just gives you scaling of some quantities and those stable quasi-particles. Everything else is, just quasi-particle physics. One very exciting point, I think it's exciting just because it tells you this is a very robust phenomenon, that it seems to be very stable to integrability breaking perturbation. I should really say that, that paper I just mentioned is probably just the first step, right? This is a very hard question. We already don't understand that phenomenon that well. And now we break integrability, which is hard. So, we have some very good indications that at least there's a sharp distinction between perturbations that break the SU2 symmetry and perturbations that do not break it, okay? If you don't break the symmetry, we think that those quasi-particles are very long-lived, and so you can still see this KPZ physics at least for experimental or numerical timescales, right? So that would explain, for example, maybe why you see it in the spin 1 Heisenberg chain. At low energy, you have a sigma model, which is integrable. So, and we think maybe it's proximity to that low energy physics that gives you what you see in numerics. Okay. Even though, again, I think that, you know, we need more work to actually make all of this more quantitative. So there are many open questions. KPZ, I mentioned this argument by Veer. You know, it would be nice to have other ways to derive it, maybe ways that are more microscopic, that we can understand how KPZ is emerging. The connection to the picture I just told you is not entirely clear. From integrability breaking, I think here there are many questions, higher order processes, whether you need anything non-perturbative. You know, what is the time scale for diffusion? You know, I mentioned that in those examples, we see t to the 1, we see z equals 3/2. I said, I believe you cross over to diffusion, but we have no idea what the time scale is because we don't really know what the leading process, you know, for decay is. So all of these are important open questions for the future. And so with this, let me thank you very much for your attention, and I can take questions.
Thank you very much for the very nice and clear talk. Okay, are there any questions or comments? Yes, Stefano, please.
Hello, here is Stefano Lepri. I wanted to ask you, first of all, if I understood correctly. So your claim is that the KPZ regime sooner or later should stop and give rise to diffusive regime for perturbed integrable system, right?
That's my belief, yes, correct.
Because I wanted to comment on the fact that if you take, for example, the classical Toda chain, it seems the situation is opposite. So you first find a diffusive regime, and then a crossover to, I mean, you can either do it in time or in the size of the system, it should be the same, right? And then a crossover to this KPZ regime. So my understanding of this was that there is a kind of a kinetic time scale on which your quasi-particle must thermalize. And during this regime, basically you have a standard diffusive process. And only on very long time, you see these KPZ effects, which after all are basically hydrodynamic type of effects. So it seems that in your model, it's just the opposite. Do you understand correctly? Or?
So, yeah, so here, like, it's important to stress that, you know, when you break integrability in that chain, right? So, you know, you only, when you break integrability, you only have like two conserved quantities left. You have energy and spin.
Yes.
And again, that, you know, in the case where you put noise, you just even kill energy and you just have spin, for example, right? And so there, you know, if you write a hydrodynamic equation, say in the case where you have noise, you know, the hydro equation you'll write is just a diffusion equation, right? And you can add fluctuations. There's no nonlinear fluctuating hydrodynamics or anything like this here, like fluctuations are irrelevant. So there's no, you know, it doesn't give you anything KPZ-like. So really the expectation would be SU2. So yeah, that's the difference. So if you write like hydrodynamic equation without integrability, you know, like I mentioned, there was this paper by Andy Lucas and collaborators. Like if you write down the hydro and you add fluctuations, you do, you know, there seems to be no way out of just diffusion.
Okay.
So that's why
the hydrodynamics is different. It's different than the, okay. This I missed this point. Okay, thank you very much.
Sure.
Okay. Thank you. Maybe next question is by Manas, please.
Hi. So can you show the plot where you had this plot when you break integrity but preserve symmetry? Right.
This one.
Yeah. So here it looks pretty robust, right? So even if you wait for long times, there could be, I mean, is there a possibility that this will just survive, or are you sure that eventually you should go to diffusive behavior?
Good. Yeah. Well, you know, I don't know if I'm sure of anything, right? Because, you know, this is just the data, and unfortunately, we cannot go to longer times. So again, the reason I believe you go to diffusion is because if you do the hydrodynamics, like I said, without integrability, the expectation is diffusion. It would be it would be very interesting or exciting if it survived, right? So I think the short answer is we don't really know. I would point out those are short time scales, right? So this is what we can do with the MRG. Once we add those perturbations, it dies after less than time 20, really. So, those are still relatively short times. So it's hard to make a very asymptotic statement based on this, right? I would say it looks very robust, and I agree. Even far from integrability, it looks really robust. I maybe what I can point out is in this case, this was noise. So I know it's different. You don't have z equals 3/2. But here you can maybe see a bit more clearly. So you see the prediction here was log t. But you see if we crank up noise, if you look at the red curve, I think you would, I don't know, I believe it saturates, right? It looks fairly convincingly saturating, and it doesn't really look like a straight line, for example. It's true in the z equals 3/2 case, we don't really see this saturation. I agree, even when we take, even when we take pretty big perturbation, I agree, we don't really see saturation, but we can also reach only pretty small short times. So yeah, my belief is you saturate eventually, but of course we can maybe leave this open, and I think it's already very interesting, even if it lasts for a very long time, right? Yeah.
Right. Because I think with Abhishek, Herbert, and Abhijit, we had a paper on classical integrable spin chain. Right. Mm-hmm. Probably there we could try to maybe add these additional perturbation terms. Maybe there we can go to longer times because it's a classical model.
Yeah, that would certainly be very interesting. I guess you had examples in your paper, right, of models that are SU2 invariant, but do not show KPZ, right? Like if you just take the Heisenberg chain.
Right. But we also
that's not integrable. You had diffusion and maybe with logs, but you don't see z equals 3/2. So at least you know those points exist, right, already. But I guess it would be interesting to do the same analysis of small integrability breaking perturbations.
Exactly. So we did not check the adding of breaking integrity terms but preserving symmetry. So maybe there we can access longer times probably.
Absolutely, that would be very interesting, and maybe you can understand. Maybe at least you can get the scaling of the time scale from that classical numerics, which we couldn't do in the quantum case. Maybe if you see crossover to diffusion, you can see how you can extract the crossover time scale.
Right. Okay. Thanks.
Yeah, that would be very interesting.
Yeah.
Okay, thank you. Abhishek?
Okay. Yeah. So one question was similar to what Manas asked. So the other question was, so if you just write the hydrodynamic equations for the at the isotropic point, so I mean the spin field, I mean, I guess it's coupled to the other fields, right? Or to the other conserved quantities, or do you expect that it's kind of decouples and then somehow you get the KPZ equation? Or
are you talking at the integrable point?
At the isotropic point.
Yeah, but in the integrable limit, right? Or
in the integrable limit.
Yeah, it's a good question. So so there's a sense in which spin decouples in some way. So I think that's that's the belief. I guess I had that nice picture I stole from Jacopo here. So there's a sense in which we believe the magnetization just obeys like a stochastic Burger's equation. That's how we believe KPZ is emerging, if you want. And that's what the argument from Veer is telling you, that there's a sense that in which those fluctuations like decouple from their own hydro equation, where the other degrees of freedom give you noise. But how that happens precisely is still pretty open. Okay, so maybe Veer would be the right person to argue this, but yes, like this, we believe that there's a sense in which it will decouple effectively. And it does play a special role in generalized hydrodynamics, I should say. But so yeah, we have like.
Okay. Yeah. Thanks.
Okay, thank you. And next, sorry, cryogenic, Siga.
Yeah, hello, thank you. I'd just like to comment about here classical simulations where you break integrability but keep SU2 symmetry. There it's actually possible to see a systematic drift towards diffusion. I mean, I had some data on this on a paper together with Tomasz already. Okay. So yeah, it is possible to observe systematic drift towards diffusion.
Okay, so you had that like small. Can you see like how the cost of the time scale was maybe scaling with the perturbation?
We didn't look at this that closely, but yeah, I think it would be possible to extract that from the data. Yeah.
Very good. Okay, thank you.
Okay, maybe I have one question. So, sure. If I understand well, so the most essential ingredient to see the KPZ behavior is to have this quasi-particle, which has lifetime of time or with order SQ. Is it
correct?
True?
Yes.
Yeah. And so this is clearly known for the case of XXX, right? And the
go ahead.
Similar behaviors are seen in other integrable systems like Fermi-Hubbard and so on. So for these, I don't know, but is it true that for these models also, so these kind of quasi-particle properties are known?
Yeah, so I don't want to steal in his thunder, but I think he's going to talk about this on Thursday.
Okay.
And he will have a talk on like So, I mean, the short answer is yes, you can, you know, there's something also super universal about the way thermodynamic beta ansatz works. And again, and we'll talk more about this. And, you know, then you have, we believe the same type of picture really works also there. Yeah.
Mm-hmm. And the related question is there possibility to see similar behavior for the case with non-integrable perturbation? Or is it just difficult?
Oh, you mean like this scaling?
Yeah.
Well, I mean, the issue is like here, again, like, you know, this whole argument requires kind of a hierarchy of quasi-particles, right? So, and, you know, like, okay, maybe if you convince, you know, in normal solid state experiments, if you convince people that you have a physical mechanism that relies on magnons, they will be happy. Maybe a bound state of 2 magnons, they will also be okay. But if you start saying, okay, the mechanism involves like a bound state of 100 magnons or 1,000, and, you know, it's asymptotic like this, people will, you know, like start questioning your sanity and why those things are like stable and do not just decay right away. So I think this is where, like, reading the arguments, I think integrability is crucial, that in order to have those giant bound states be relevant, especially at high temperature, you know, you need integrability. But again, it could be that those bound states are very stable in real life as well, because of, you know, they are pretty stable to integrability breaking.
And also, if there was some model system which has this kind of property, which is not due to integrability, then would it also show the KPZ behavior, you think?
Yeah, so, you know, in some way, like I said, the argument doesn't really rely too much on integrability beyond again, having those quasi-particles. So I think I should say, so this KPZ scaling is one example. There are other examples of anomalous behavior in integrable spin chains that really rely on having this hierarchy of quasi-particles. So having this hierarchy of quasi-particle gives you a pretty natural window to have anomalous behavior. So this is very true. And so if you had like a, you know, different model, a toy model or something that had, again, kind of a hierarchy of quasi-particle. So hierarchy in a sense that, again, like you have here, you could label them by S and the velocity scaled in some way and so on. So yes, I think if you took a completely classical system with the same parameters of velocities and so on, and this, yeah, you would, you know, you could reproduce this, this anomalous transport. So I think it gives you I'm going to say new, at least I you know, I didn't find anything that resembled this in the literature, way to get anomalous transport from having this, this hierarchy.
Okay, thank you. Okay, it's more or less time for, but if there are one or two short questions, maybe we can get them. Maybe not. If there are no further questions, yeah, let's thank Romain again.
Thank you.